You're a sweet little headache, but you are lots of fun. I've a good mind to spank you, then thank you for all you've done.
Welcome to our 23rd lecture in Chemistry 51C here at UC Irvine. This is the quarter of the year of the coronavirus shutdown, and we're in the final 2 weeks of the quarter. I ran across the term blurb recently, and I wanted to find out, where does the word blurb come from? And I tracked it down to the dust cover of a book that was published in 1907. It was a book by Gillette Burgess. And I wasn't sure what to be more interested by, maybe the word blurb. This is a book from 1907, or by this freaky picture of this character named Miss Belinda Blurb. But what really caught my attention was the title of the book, which is Are You a Bromide? And the full title of this book is Are You a Bromide? Or The Sulfitic Theory, expounded and exemplified according to the most recent researchers into the psychology of boredom, including many well-known bromidiums now in use. What a long-winded title. But, it took me down this rabbit hole of Gillette Burgess and bromide and bromo-seltzer, and ultimately to an organic compound called acetanilide, which was used as a pain medication, over-the-counter pain medication, pretty widely in various different products. So I'm going to talk about this one particular over-the-counter pain medication they sold in packets on drugstore counters called Orangine. And, the name of this powder, Orangine, it kind of implies that there's going to be some sort of an amine in here because it's called Orangine. But that's not really the important component of these powders. They're quite upfront that there's no orange at all in Orangine powders. The stunning thing that is that they're very upfront about the fact that it contains this molecule acetanilide. This is an old-fashioned spelling or a German spelling. But what's more interesting is when you look at the back side of these powder packets, these Orangine powder packets, they tell you the composition to some extent of what's in here. It tells you that these Orangine packets contain acetanilide. They're measuring it out in grains, which is a pharmaceutical composition unit. I don't know how that relates to grams. They tell you it contains caffeine. That sounds like it's good for headaches. But what's more astounding is they tell you they're using a trituration, a mixture of blue flag, that's iris flowers, that's toxic, and mandrake, well known as a toxic plant, and nux vomica, also known as the strychnine tree, which is where you get rat poison, is strychnine. Why they would be putting those things in there is completely beyond me. Maybe people feel that if it's from nature, it's somehow healthier for you. That's ridiculous. A little bit disturbed by those, but I'm interested in acetanilide and what is the evidence that that's actually going to cure any sort of a headache that seemed to have been present in a number of different over-the-counter formulations. So let's talk about acetanilide. And first, we'll talk about why it might be toxic, and then maybe why it would cure headaches. So acetanilide is a derivative of aniline. It's an amide that you would make if you acetylated aniline using acetyl chloride or acetic anhydride, very inexpensive to prepare. And the reason why it's toxic is that when you ingest acetanilide, 1% of that acetanilide is getting metabolized by the human body. The human body has proteases all over the place. Acetanilide is not a normal substrate, but can be processed at slow rates. And the amide bond can be cleaved by those enzymes to give you aniline. And that's the start of toxicity, because you don't want to be taking drugs that have aniline in them. Aniline gets further metabolized to a hydroxylamine through formation of an NO bond. And that compound, or its further metabolite, binds to hemoglobin, and it prevents hemoglobin from carrying oxygen around the human body. It leads to this rather embarrassing, actually dangerous complication called methemoglobinemia. You can see the impact of not being able to carry oxygen around in your body if you've got methemoglobinemia. And people reported these problems. Quite a few people died from ingesting these orangine powders. What's a little bit disturbing is the packet says if your headache isn't cleared up, then take another packet in half an hour. And I can imagine people repeating that, which maybe is a little bit sad. But what's interesting is that acetanilide, there is good reason to expect it to cure your headaches. Where does the other 99% of that acetanilide go when you put it inside the human body? It turns out that it gets metabolized by enzymes, mostly in the liver. These are called cytochrome P450s. We talked about those at the beginning of the last lecture, which oxidize foreign-looking molecules. And those enzymes put a hydroxyl group at the para position of acetanilide. We don't have any chemical reactions that we're going to teach you that allow you to do that in one step. But these enzymes do that. And it turns out that this compound is not toxic. And it was marketed in 1953. The Sterling Winthrop, the pharmaceutical company, recognized that, well, if acetanilide is toxic, why don't we just sell them the metabolite, the one with the parahydroxy group, which is not toxic, and which is actually the thing that cures the headaches. And that was sold as Panadol. But you might know that under a more common name, because here in the United States, I think that was marketed by Johnson & Johnson as Tylenol. So that's Tylenol, also known as acetaminophen here in the in the United States, or paracetamol over in the UK. So again, the people who are taking these orangine packets or bromo seltzer that had acetanilide in there were taking a precursor, a metabolic precursor to Tylenol, to acetaminophen. So very interesting. Let's go ahead and bring ourselves back to where we've been in our course here. We're just about to finish up the last chapter, full chapter that we're covering today. So hopefully I can finish up the lecture rather shortly. And the last thing that we're going to do is we're going to cycle back to an earlier chapter on the substitution of aromatic rings. And probably we won't get to that until Friday. But let's go ahead and try to finish up our work discussing amines and the chemistry of amines. In this last section of the book, here in chapter 25, has to do with the chemistry of benzene rings that have a particular functional group attached to them called a diazonium functional group. Let me try to sketch that out of the top so I can introduce to you why am I covering the reaction of amines with nitrous acid. We're trying to talk about this freaky looking functional group called a diazonium group. And so let's go ahead and see how nitrous acid fits into that. So you can't buy nitrous acid. This is something you have to make as a reagent in the laboratory, kind of like LDA. You have to make it yourself, except it's easier than LDA. You simply mix together sodium nitrite. It's just a common white powder that you can buy in the salt form. And when you mix that with hydrochloric acid, which we have readily available in every laboratory, this is a reaction that occurs in water, you end up forming nitric acid in solution. So you're simply protonating the sodium nitrite to generate nitrous acid. And nitrous acid is unstable. And it forms, if you create solutions of nitrous acid, they're unstable. That's why you can't buy it. The other byproduct that you get out of this is sodium chloride, but that's not interesting. And this unstable nitrous acid is in equilibrium with, this species called a nitrosonium ion. Let me go ahead and sketch out this nitrosonium ion. Here's the nitrosonium ion. Whoops, I got the charge in the wrong place. Let me fix that. There we go. 3 bonds to oxygen needs to have a positive charge. That's a nitrosonium ion, this species right here with the NO+. And that's extremely reactive, that nitrosonium ion. Let me go ahead and draw a little label line here. That thing right there is the nitrosonium ion. And it reacts with nucleophiles, even mildly nucleophilic stuff. Let's go ahead and talk about the mechanism for this nitrosonium ion, because I don't think you could figure this out, right? Let me go ahead and draw out what's going on with nitric acid and why it's so unstable. When you create solutions of nitrous acid, of course, they have to be under acidic conditions for you to have solutions of nitrous acid. Acids can catalyze this decomposition to form a nitrosonium ion. So let me go ahead and draw that out. So if you have nitrous acid in the presence of acid, you protonate the nitrous acid. Now, the logical place to protonate the nitric acid is right here on that nitrogen, and that's happening. But that doesn't lead to the nitrosonium ion. It's only when we draw the lone pairs over here and we protonate that we're going to be able to explain how you form the nitrous acid. So there's lots of lone pairs on nitrous acid. They're all being protonated and deprotonated. But when we protonate that HO group, that's when we can go down a pathway that ultimately leads to nitrous acid, because now we've created a leaving group, H2O plus. And this oxygen over here has lone pairs. The nitrogen has lone pairs too, but you're not going to use those for the arrow pushing. So the oxygen lone pairs are positioned, they're poised to push out that water as a leaving group. And that's what leads to the formation of these nitrosonium ions that are so electrophilic. And so what happens if you take an amine and you mix it with nitrous acid? You get a reaction. The small amount of nitrosonium ions that are present there react with amines. Let's go ahead and follow through that pathway. Let me go ahead and take an example here where I take some sort of an amino group. I'll make it a dialkylamine, but it would also happen to a primary amine. But in this case, with a dialkylamine, we get a readily isolatable product. There's a lone pair over here. And so you can imagine if you have a nitrosonium ion like this, that we're going to get some sort of an addition to that nitrosonium ion. And that's exactly what happens. So there's that nitrosonium ion being attacked by an amine. And if you follow my arrow pushing, I should now have a double bond to the nitrogen. And there should be a plus charge over here. I have 4 bonds to nitrogen. That should have a plus charge. There's still going to be this A- counterion floating around there, so I might as well just draw that. And that's going to pull a proton off of the amine that just attacked the nitrosonium ion. And so this leads to a species that just immediately looks dangerous to me. The two R groups can be different, right? It could be R and R prime. N-nitroso compounds are well known in the chemical literature. These tend to be carcinogenic. There's a book called Toxic Love about this psychotic dude who tried to poison his girlfriend and her family tried to give them cancer by dosing them up with these N-nitroso compounds, and specifically N-nitrosodimethylamine. What's a little bit disturbing is that this N-nitrosodimethylamine is a potent carcinogen, or N-nitroso compounds tend to be carcinogens. The sodium nitrite is a common preservative in bacon. And of course, hydrochloric acid is the acidic component of the human stomach. And these lead to N-nitroso compounds, which are carcinogens. But if you look carefully at the bacon packets, they put a preservative in there, which inhibits the formation of these N-nitroso compounds. Pretty brilliant. So I still worry a little bit when I eat bacon. Maybe not as much as I ought to worry, I think. Let's see what the fate of nitrous acid when one of these R groups is a phenyl and one of the R groups is an H. In other words, aniline. So let's go ahead and take a look at the addition of anilines to these conditions that contain nitrous acid. So let me go ahead and sketch that out here. I'll go ahead and start off by drawing aniline. We're just worried about the NH2 group on aniline, so I'll abbreviate the phenyl group of aniline. And when we treat this with nitrous acid, and again, we can't buy nitrous acid. We have to make that in solution. So this is the way you write it out. It's kind of like hydrocyanic acid. You have to buy sodium cyanide and you mix it with HCl. I'll put the HCl underneath here. These are always aqueous conditions. And what you get out of this reaction is not that N-nitroso compound. It keeps going further to form a species called a diazonium ion. And you haven't seen these before, but they turn out to be very important synthetically and very important in the history of the pharmaceutical industry. So this is a diazonium ion, and this particular one, because it's a phenyl derived from benzene with no substituent, is referred to as benzene diazonium. That's the unsubstituted version. Maybe I'll write that out so you can see the name. This is called benzene diazonium ion. And if we're referring to the fact that it just happens to have a chloride salt, I'd call that benzene diazonium chloride. But really, benzene diazonium is the chloride. You can make these with other counter anions, and they'll have the same type of reactivity. Let's go ahead and walk through the mechanism for this. What's the mechanism for formation of this benzene diazonium ion? So down below here, let's write the mechanism. Now, I'm not going to redraw the mechanism for forming the N-nitroso compound because I just showed you that on the last slide. I don't need to re-show you how you get an N-nitroso compound. But what happens is that as this stirs around under acidic conditions, it keeps going. So let's go ahead and watch what happens as this N-nitroso compound derived from aniline reacts further with acid in those solutions. So I'm going to draw out, of course, the acid can protonate all kinds of lone pairs here. I'm only going to draw the events that lead to the formation of this benzene diazonium ion, and that starts with protonation of oxygen. Obviously, if you want to make a diazonium ion, we've got to get rid of that oxygen somehow. And so mechanistically, we're going to start by protonating the oxygen here. And so now that's going to lead to this protonated N-nitroso aniline. And we're going to draw our counterion here, this A- counterion, and we're going to deprotonate on this bottom proton. Now watch the arrow pushing here, because what I'm going to do is I'm going to take the electrons in this HN bond and I'm going to push them all the way to this nitrogen to make an NN double bond. And then we have to break the NO pi bond at the same time. And so now we're getting very close here. And now, because we're still under acidic conditions, we're going to protonate the OH and turn it into a leaving group like this. I'm running out of room just a little bit here. But you can see I've created a good leaving group by protonating that oxygen, that OH. Now I've got water as a leaving group. And now I can draw the protons on the opposite side there, and they're simply going to push out that leaving group like that. And that's what leads to this benzene diazonium ion. And if you're doing it in HCl, the counterion is chloride. So you can make solutions of these benzene diazonium ions, and then you react them right there in the flask. You don't even bother to isolate those. That would be pretty rare. Okay, let's go ahead and walk through a sequence here where you make a benzene diazonium ion, and then I'll show you some cool reactions that you can do with that. And I'll remark on the character of that, what strikes my fancy when I see that N2+. So let's go ahead and start off with a benzene ring, right? Because this will remind you of synthetic chemistry that you've already seen. If you start with a simple benzene ring and you want to put lots of amazing functional groups on there, we're going to start with nitrogen. So you only know one reaction that adds a nitrogen carbon bond to a benzene ring, and that's nitration. So let's go ahead and start off with that. So step one, I'll put regular Arabic numerals because you would typically isolate these intermediates. Do you remember the conditions for nitration of a benzene ring? It's nitric acid and sulfuric acid. And then we told you how to reduce that nitro group down, right? We don't really want the nitro group on there. We want the anilines. We can do this diazonium chemistry. So step two here would be H2 and palladium on carbon. That's a catalyst. And that would convert the nitro group into an amino group. And now we can do this diazonium business. And so what's the reagent systems that we just learned here? It's sodium nitrite in hydrochloric acid. And that's how you make a benzene diazonium ion. Now, when I see this benzene diazonium ion, it looks like nitrogen gas. There is no more stable molecule that we're going to teach you about than nitrogen gas. Is the least reactive, most stable molecule. As far as leaving groups go, it's the best leaving group you will ever see, in spite of the fact and let me draw the counter ion under these conditions as chloride. If I asked you to draw the product and you made this in HCl, I would expect you to draw a chloride counter ion. You can't just draw a cation with no, you can't isolate just a mole of cations. So we have to have a counter ion to that. You know, what's weird is that you've got this great leaving group. And in spite of the fact that we have this amazing leaving group, nitrogen gas, what could be a more stable, less reactive leaving group? You have to avoid this thinking that this will ever actually leave. Even though it's the most amazing leaving group ever, here's what will never happen. You're never going to just simply ionize this off, because the cation that you would generate, the carbocation, let me draw it edge on, would be so hideous looking. I don't want to say that this happens. It doesn't happen. But this carbocation, if I draw it edge on, is completely unstabilized. You would end up with a carbocation sticking off the side of the benzene ring with no electrons. That's not stabilized by resonance. You can only stabilize benzylic carbocations that are next to benzene rings. But a carbocation that's sticking off the side of a benzene ring that's sp2 hybridized, that's less stable than a primary carbocation. I'm going to just write that there so remember. So less stable than a primary carbocation. Meaning you're not going to be making that phenylcation. Benzyl, where there's a phenyl attached to a methyl cation, yes, but not a phenylcation. That's a phenyl and benzyl are completely different. Even though benzyl sounds like benzene, this phenylcation is not makeable under any circumstances as a mechanistic intermediate. Okay, so how are we going to use this benzene diazonium or arene diazonium, these types of intermediates? In fact, there's a number of different reactions that are very useful. They're transformations that you need to know. Okay, here's 5 super useful transformations of arene diazonium ions. And why would you care so much about putting substituents onto benzene rings? Because when you look at the drugs that are prescribed, the orally available drugs that are prescribed in the United States, most of them contain aromatic rings. And so you need to know methods for how they construct those types of medicinally important molecules. The first reaction I'm going to show you is one in which we use this arene diazonium group for electrophilic aromatic substitution for formation of carbon-nitrogen bonds. So this is kind of weird because the benzene diazonium is kind of the reagent, but I'm going to draw it here as though it's the starting material. And we can use that in electrophilic aromatic substitution reactions. I just take a nucleophilic benzene ring. Let's pick one that's activated here. So just looking at this, at the way this is drawn out, if I wanted to form this bond, what I would want to do is add cresol in there, an activated benzene ring. And if you have an activated benzene ring, in this case, the more powerful activator is hydroxy, and so that would drive substitution at these 2 ortho positions. It's the more powerful activating group controls the regiochemistry, and so it doesn't matter whether you brominate, nitrate. You're going to, the next electrophile is going to add ortho to the hydroxy group, and in this case, look what you do. You form this functional group. There's a functional group that we've just created here, called a diazo functional group, or actually not diazo, sorry. Let me take that out. I'm just going to call that an azo functional group. That NN double bond is an azo functional group. And anytime you have a food that has food coloring in it or a dye in it, in most cases, those are synthetic dyes and they contain azo functional groups made through this chemistry that I just showed you. So whether it's Kool-Aid or some colored drink that you buy as a soda that's yellow or red or green or something, those are usually azo dyes that are made synthetically. Okay, what are some other powerful transformations that you can do using arene diazonium ions? You can make, if you can nitrate something, you can hydrogenate it and then convert it to a diazonium ion. Here's a powerful transformation, and that is putting on oxygen bonds onto benzene rings. We haven't shown you any reaction. This is the only way we're going to tell you for making oxygen substituents on benzene rings. And that's to first make an arene diazonium ion and then treat these with water. Typically, you would heat these, but the book doesn't talk about that, so I'm simply going to add water in here. We're not going to talk about the mechanism. If you think you know the mechanism, we haven't taught you enough to think about that mechanistically. Don't worry about it. But just assume that if you put this in water, and I'm not going to make you draw heat, but obviously you synthesize these in water, so it's not super fast and spontaneous to convert this to a phenol. But arene diazonium ions are the only way for you to make a phenyl oxygen bond. You can't directly put on oxygen using electrophilic aromatic substitution in one step. What's another functional group we haven't taught you how to put on a benzene ring? Well, another one would be fluoride. We haven't taught you, right? We taught you how to put bromine on a benzene ring. We taught you how to put chlorine on a benzene ring, like Cl2, FeCl3. We have not told you how to put fluorine on a benzene ring. And there are lots of drugs that contain fluorine substituents on benzene rings. And here's the secret recipe. It's tetrafluoroboric acid. You can buy solutions of tetrafluoroboric acid. It's generally written out like this, HBF4. The real way to think about tetrafluoroboric acid is that it's kind of like boron trifluoride that's been mixed with hydrofluoric acid. And I'll draw it like this, but really the proton is bound to one of those fluorides. It's HF coordinated to BF3. And BF4 minus is a fluoride donor in this reaction. So HBF4, you don't really need a space between the HBF4. So, so tetrafluoroboric acid, HBF4, replaces a diazonium group with fluoride. This is the only way to put fluoride on a benzene ring. We're not going to teach you any other ways to put fluoride on a benzene ring. Another substituent that seems obvious, but we didn't tell you how to put it on a benzene ring is iodine. We didn't teach you how to make carbon-iodine bonds off of benzene rings. This is the only way to do it, is to make a diazonium ion and to treat that with an iodide salt. And the book tells you to use potassium iodide. It's a little more naked than sodium iodide. And that's how you make a carbon-iodine bond. You can't use I2 and FeI3. That's not going to work. So this is really what you need to do to make a simple aryl iodide. So see how powerful diazonium ions are. They're your entry to a whole set of substituents that you can't make directly through electrophilic aromatic substitution. And the last transformation that we'll cover right here is a little bit tricky because it replaces an NN triple bond with a CN triple bond. And we need a particular reagent for this. It's a copper reagent called cuprous cyanide. So copper cyanide. Copper in the +1 oxidation state, copper 1, cyanide -1. Cuprous cyanide. Copper actually can transfer a lot of groups to diazonium ions, but this is the only unique one that you need to learn about. Okay, 5 powerful transformations. You can't directly add, right? We haven't shown you any other way to put cyanide groups directly onto benzene rings. We haven't shown you any other way to put fluorine bonds directly onto benzene rings. I'm not sure if we've talked about how to iodinate super reactive benzene rings, but this diazonium thing is the only general way to put iodine onto benzene rings. We haven't taught you how to put hydroxyl groups off of benzene rings. This is the only general way. So, right? So you need to remember these recipes in addition to the recipes you already learned for nitration, bromination, chlorination, acylation of benzene rings, sulfonation of benzene rings. And now here's this second way to form carbon-nitrogen bonds by reacting with arene diazonium ions. I want to talk about specifically this the formation of these azo compounds, because they're so common in the food additives that we have and in the origin of the pharmaceutical industry. The pharmaceutical industry was started by people wanting to make colored compounds like dyes. And so let's go ahead and talk about this azo reaction. The mechanism for this is something you already know about. The mechanism for this reaction is simply electrophilic aromatic substitution. So it may not be obvious to you, but this group over here is an electrophile and can react just like the other electrophiles that we learned about in electrophilic aromatic substitution. And so that means if this thing is reacting as an electrophile, then we need to know where it's going to substitute the other the other component, which is always an activated aromatic ring. So in this case, I'm showing you resorcinol. It's got 2 hydroxy groups, superactivated. These 2 hydroxy groups are orthopara activators. So I would expect you to know that these activate orthopara. And so that means these positions here and here are the most reactive, not the meta position. And remember, we gave you this kind of obscure rule. Don't substitute in between the 2 groups. If you're given a choice, react here or here. So let's go ahead and follow through the mechanism for what's happening in this electrophilic aromatic substitution. We haven't really talked about that in a while because we've spent so much time talking about enolate chemistry. Let me use my red pen here for the arrows. So you attack here. I got to stop here because if I didn't show you this, and if I put this on an exam, it's going to trip you up because I think you're going to want to, in your brain, attack the thing that has the positive charge. Don't do that. Don't attack the atom that has the positive charge. I know you want to do it. I know you want to. Don't do it. Attack right here on the end nitrogen. There we go. And push the electrons in the triple bond to the nitrogen that has the positive charge. You've got to practice that or you're going to mess it up because it's so natural to want to attack the nitrogen with the positive charge because you might think it's like a carbocation. It's already got too many bonds. Attacking it with making another bond isn't going to make it happy. Too many bonds. That's why it has the positive charge. Okay, so don't attack the N+. So this is going to lead to this intermediate. I'm going to abbreviate that phenyl ring on the left side here with just writing it phenyl. And we've broken that triple bond, and we've made a bond to the nucleophilic aromatic ring. That's going to leave a positive charge. Ooh, wow, messed that up. There we go. And there's an H here. Let me draw that H. I'll need that shortly. There was an H there when we attacked. There's still an H proton right there, and we're going to need to pull it off. I've still got the counter ion left over. These are run under acidic conditions. So I'll just draw a mechanistic version of our conjugate base here. I'll draw A-, and that deprotonates to regenerate aromaticity. Let's go ahead and draw that out. There we go. And that's the mechanism. It's just 2-step electrophilic aromatic substitution. But it's going to look unfamiliar because it involves this phenyl diazonium. And here we are at the end of the quarter, and you haven't had 3 months to practice that. So let's take another opportunity here to practice that. Let's draw another example. And maybe I'll try to put this into, not another example, I want to put this into the context of why should this look a little bit familiar and yet a little bit unfamiliar. When you attack arene diazonium ions, let me circle that charge so we can better see that it's there, with some sort of a nucleophile, this is actually a little bit similar to arrow pushing that you've seen before and a functional group that you've seen before. So this process of attacking, don't attack the N+, attack the nitrogen, and then push the electrons to the N+. This should look a little bit similar to something else that you've already seen, and that's acylium ions. Remember, acylium ions also have this, can be drawn with this triply bonded functional group. And in that case, we had a plus on this oxygen, and we don't attack the oxygen. The oxygen has too many bonds. We don't want to make another bond to oxygen. We want to give it electrons. We don't want to give it another bond. So if you had that same electrophile or some other reactive electrophile, nucleophile, then again, we don't attack the oxygen. We attack the atom next to the O+. And so the arrow pushing is similar, but notice how the R groups are attached in a different position on these triply bonded functional groups. So I hope that looks a little bit familiar to you. That arene diazonium looks a little bit similar to an acylium ion. But again, we're at the end of the quarter and you've had almost no time to practice this. Work problems in the sapling problem set involving diazonium chemistry. And try to get used to this arene diazonium chemistry. Okay, we've reached the end of chapter 25, and at the end of chapter 25, they talk about the synthesis of synthetic dyes, which is really just a review, should be a review of this diazonium chemistry, using arene diazonium ions for electrophilic aromatic substitution in order to make these azo linkages. This is called an azo linkages. And dyes that have two phenyl groups on azos are called azo dyes. We are not going to talk about the synthesis of sulfa drugs, just because those are really, I mean, from the 1930s and 1940s, and they haven't been important, um, in 80 or 90 years. So why talk about those? But it's interesting to read. I'm just not going to ask you questions about that. All right. We're going to stop right there. That finishes the last chapter that we're going to cover. When we come back on Friday, I'm going to cycle back and bring you back to chapter 18, and we're going to talk about a type of aromatic substitution where instead of using powerful electrophiles, we use powerful nucleophiles. And I didn't feel like that material fit until we covered acyl chlorides and nucleophilic substitution of carboxylic acid derivatives. It didn't make sense to me to cover that until we finish chapter 22. So we're going to circle back to chapter 18, finish that out, and that's going to be all the new material for the course. So please stay engaged in our class. Go to discussion sections, go to office hours, work problems, work every problem you can get your hand on, work them yourself. And it's okay, to get things wrong and try over and over. That's going to teach you how to work problems you haven't seen before. And so I will see you guys on Friday.